With this EEG, we will show the evolution from wakefulness to sleep. In the early part of this segment, we can count a posterior basic rhythm at about 9 to 10 Hertz. It shows a slight spindle shaping or modulation, and it is called a modulation of the alpha rhythm, and it predominates over the posterior head regions. Nonetheless, the patient is probably drowsy as there is some interspersed beta activity and relatively slow eye movements. As we move forward in this recording, we can see a transition to drowsiness. At this point, that well-sustained posterior alpha rhythm, spindle-shaped, is now attenuated and is beginning to fall out. In addition, the baseline is wandering and there is some underlying delta activity and theta activity with the progression of drowsiness. In the next segments, we can now see appearance of these triangulate potentials over O1 and O2. Here on the right side, delineated by the black arrow, and on the left. In fact, they are present here, here, and here. Here's another example on the left, and an example both on the left and on the right. These are positive occipital sharp transients of sleep, or posts, and typically appear in stage 1 sleep and may persist in stage 2 and even later in sleep. As we progress in this recording, we now notice that the alpha frequency patterns have moved further anteriorly. They're no longer over the occipital region. This occurs either with drowsiness because mu rhythms are appearing, or because there is a transition with the appearance of sleep spindles. We will see this more clearly later on. At this point, towards the end of this segment, we can see a phase reversal at C4 and at C3. This is a vertex sharp wave. Vertex sharp waves are seen at the end of stage 1 sleep, but also persist in stage 2 sleep and later on. At this point, there's a much more clearly delineated vertex sharp wave and the appearance of faster frequencies shortly afterwards. These are sleep spindles. The vertex sharp wave, in concert with the sleep spindles, have been called K-complexes. Here is a much more clearly defined vertex sharp wave with the following sleep spindle. Now we see better defined sleep spindles which may be slightly asynchronous or asymmetric, but on the whole should remain equally well represented on both sides. Over the posterior head region is a much more clearly defined positive occipital sharp transient of sleep seen here synchronously bilaterally. We end up with some vertex sharp waves, intervening sleep spindles, and 2 K-complexes, typical of the progression from wakefulness to sleep. Brief segment. We use an antero-posterior montage, parasagittal over temporal. With the black arrow, I'm demonstrating a frequency at about 8.5 cycles per second, or 8.5 Hertz. As you can see, it is present in this case bilaterally. This is in the alpha frequency, but in fact, for this burst of alpha frequency here, it is not over the occipital region and therefore does not represent the alpha rhythm. In effect, this is not the posterior basic waking frequency. This alpha frequency pattern over the central head regions represents the resting rhythm of the motor strip. It is called the mu rhythm. Not infrequently, this is seen asynchronously or even asymmetrically, being present only on one side. It is usually seen during wakefulness or mild drowsiness. One way to test the nature of this mu rhythm is to ask the patient to move or think about moving their contralateral arm. In that case, the resting rhythm disappears and the mu rhythm is blocked. Over the next several segments, we will see how this mu rhythm evolves. Here we can see that with increasing drowsiness, in fact, the mu rhythm stopped after the first second of this 10-second segment. When the patient was aroused, here as evidenced by muscle artifact and eye movement, we can see that the mu rhythm is not clearly in evidence, nor is there in fact a posterior alpha rhythm, but towards the end of the recording we can see the appearance of the mu rhythm over the central head region. Once again, the best illustration that mu rhythm is the resting rhythm of the motor cortex is to ask the patient to move the contralateral arm. Over the right temporal derivations, there is a potentiated pattern of beta frequencies seen here, some slightly sharply contoured but lower voltage beta frequencies, and some discharges, as it were, in the alpha range. If you look more closely at the morphology, you will see that there is a notch pattern. Here the black arrow shows the notch, then the potentiated alpha frequency, then a notch, another potentiated frequency, and now for the next three waveforms, notches that appear at different parts of the alpha wave. Here on the upside, here on the downside, and on the next wave also on the downside. The third wave also has a notch on the way down. These are typically produced by two frequencies that are encountering each other. On the one hand, you have alpha frequencies that dominate the voltage in this segment, but they would be encountering beta frequencies here revealed by the arrow and potentiated towards the end of this 1 second segment. When both frequencies are present, the interference of the beta frequency in the alpha frequency will produce the notch either on the way up at the apex or on the way down. You can see an example of this to the far right of this 10-second segment. Some of these notch patterns, when slower and occurring during drowsiness, appear as rhythmic mid-temporal theta during drowsiness and have been called the psychomotor variant. In older populations, when they are more arcuate and more posterior over the parietal regions, they have been named wicket spikes because of their resemblance to the wickets used in croquet. As we go along these segments, we will see an evolution of different morphologies. Here they are sharply contoured, but the frequency is a little bit too high to represent a wicket spike. Over here, we can see the notched rhythms that would be typical of the psychomotor variant. Again, an alpha frequency encountering a beta frequency. The notched pattern is very well shown here. As we move to the next 10-second segment, we see some potentiated waves here towards the last second. We would have to decrease the gain to be able to see them more clearly. Here we can see that in fact, when resolved, they possess a notched form and therefore represent a benign pattern. At 15 microvolts per millimeter, let's progress for further segments in the recording. Here we have an example that closely resembles rhythmic mid-temporal theta of drowsiness. They are triangulate, they do not possess clear spike wave morphologies, and even though there is a field, they appear to build up and go away in a progressive fashion. These, however, increase and decrease during the course of a fraction of a second, not over seconds to minutes, as may be seen in epileptiform discharges. Nonetheless, wicket spikes may persist for several seconds and wax and wane during a recording, and rhythmic mid-temporal theta during drowsiness can also last for minutes during a drowsy recording. As we get towards the end of this recording, we can see the different patterns appearing. Here's the notched pattern of the psychomotor variant. Here would be one that could equally apply to either the psychomotor variant or rhythmic wicket spikes. In summary, one of the major determinants of benign rhythms is the notched shape of the theta or alpha frequencies. They will wax and wane, and even though there is a field, and occasionally they may potentiate, the presence of higher and lower frequencies encountering each other is a hallmark of a benign rhythm. This is an interesting and rare phenomenon on EEG. The patient had fallen while mowing his lawn, had a pacemaker in place, and remembered feeling faint. Nonetheless, an EEG was requested on the outside chance that he had an epileptic disturbance. The EEG here shows absence of alpha background activity, most of the activity lying in the beta range, and the absence of eye blinks. This inferentially tells us that the patient is drowsy and in stage 1 sleep. As we go towards the last half of this page, some sleep spindle-like activity and possibly vertex sharp waves are now being seen. However, as we get to the far right of this EEG display, and if I advance by 1 second at a time, we will see that there is a generalized blunted morphology seen over the frontal and central head regions, synchronously, bilaterally, perhaps less well seen over the temporal derivations. This discharge is seen here, again, less than a second later, and in different fashions over the subsequent seconds. As we advance 1 second by 1 second, we can see that this blunted discharge, seen synchronously bilaterally at about 1 per second, will increase in frequency. Here, now to 2 to 3 per second for this 8-second segment. And now accelerating to 3 times per second and perhaps 4 or more times per second. Towards the right of the screen, we can now see the increased frequency sustaining up to 8 times per second as it then fades and the patient returns to sleep. Let me return at 10-second segments to the beginning of this recording to show the phenomenon somewhat more rapidly. Once again, we're starting here with drowsiness, the appearance of stage 2 sleep, and over here on the right side, the beginning of this phenomenon. We will advance quickly, and we can see the discharges accelerating bilaterally towards the end of the recording. This is known as SREDA, or subclinical rhythmic electrographic discharges of adults. This is a benign pattern which occurs in asymptomatic patients and represents an incidental finding in a patient referred for EEG. We can see that as this pattern abates, it returns to a drowsy pattern that was seen at the beginning of this EEG. I will now progress further on in the recording To illustrate the return now to drowsiness and wakefulness, and some of these intermittent discharges seen over the central head regions. So in summary, this is a pattern of rhythmic discharges, sometimes seen asynchronously, at other times synchronously, during which time the patient exhibits no symptoms. If the patient is drowsy, they will report no change in their thinking, and if tested, will awaken and not show any evidence of confusion. This brief EEG segment shows a period of mild drowsiness. There are bifrontal eye movements seen here, shown with the black arrow. There's a posterior basic rhythm that varies between beta activity and some alpha frequencies. There's a slight hemispheric asymmetry in voltage of the faster frequencies. Here, they are a little bit higher voltage than in the contralateral side. We've been recording at a decreased sensitivity, so let's increase the voltage of the EEG. Now we have been able to enhance the voltage of the higher frequencies over the right frontal region compared with the left. This voltage asymmetry will be seen to continue throughout this recording. As we go to the next 10-second segment, we can see an eye blink towards the end of the page, and in the next segment, the appearance of alpha frequencies interspersed with these beta frequencies. These asymmetries between the left frontal and the right frontal region do not represent pathology. When there is enhancement of voltage of beta frequencies, but occasionally alpha frequencies, these are frequently seen with a breach in the skull. This is called a breach artifact. Some people believe that this voltage difference is due to the fact that skull typically, when present, for example on the left side, will absorb higher frequencies and will attenuate, therefore, the voltage seen at the scalp surface. When there is a window through the skull and the skull is not present, then higher frequencies will not be attenuated and will appear at higher voltage over the scalp surface. The EEG becomes abnormal, however, if there is slow activity. By slow activity, we mean theta and delta activity, which intrudes on the background and disturbs the baseline. Here we can see, as I show you with the black arrow, the baseline remains flat, superimposed upon which we see beta frequencies and some alpha frequencies. Here, in fact, there's a mixture of both, with a notch at the top of each alpha frequency or fast theta frequency. There's no disturbance in the baseline, and therefore this does not represent slowing or some focal cerebral problem. These arcuate in shape without a spike slow wave morphology, do not represent epileptiform morphologies and therefore epileptiform discharges. As we go towards the end of the recording, we can see these patterns wax and wane and alter slightly with wakefulness and arousal. At the bottom, the slightly spiky and somewhat arcuate pattern is really a superimposition of muscle artifact firing at T4 electrode. Also of note are the eye blink artifacts seen synchronously bilaterally that are projecting a very narrow field. By this we mean that at the very next derivation, not much more than about an inch away, there is no disturbance in the baseline, and therefore this slow wave is a near field phenomenon projected by the eye as the positive cornea moves up towards the FP1 electrode and towards the FP2 electrode synchronously with upwards eye movement. At the beginning of this EEG sample, You can see, outlined by the black arrow, rhythmic activity initially in the delta range. The frequency of this activity is 1.5 to 2 cycles per second, or 1.5 to 2 hertz. It is distributed over the anterior head regions bilaterally, and actually, in addition, there is theta activity diffusely over the central and posterior head regions. In the first 3 seconds of this sample, you can see faster frequencies here at C3P3 and to a lesser degree at C4P4. In the 12 to 14 Hz range, these probably represent sleep spindles. In effect, the first part of this recording, the first 3 seconds, are obtained during sleep. When you have diffuse slow activity during sleep, it is often not possible to distinguish sleep causes of slowing from diffuse cerebral dysfunction causing slowing. However, the answer becomes much clearer here at the beginning of the 4th second. We see incidentally anteriorly on the left the muscle artifact that occupies the first 2 channels. This occurs as the frontalis muscle contracts and muscle action potentials are produced. At the same time, we now see a resolution or regression of this sleep spindle activity, as it is no longer present in the same derivations further along here. Nonetheless, we continue to see this anterior rhythmic and sometimes polymorphic delta activity representing the diffuse slowing seen in this recording. If we now advance by 10 seconds, we will be able to see how this activity is sustained, sometimes with background theta activity, at other times, as the delta activity is enhanced, there is fallout of faster frequencies. Nonetheless, bilaterally and particularly anteriorly, slow activity waxes and wanes in this EEG reflection of diffuse cortical and subcortical dysfunction. This EEG was obtained in an intensive care unit. It is remarkable for the absence of movement and muscle artifacts. This patient experienced severe hypoglycemia and is in coma. The most marked features here are the diffuse slowing of background activity. Even when the patient is stimulated, activity rarely exceeds about 6 cycles per second. We can see here the sinusoidal morphology of the background activity at about 6 Hertz. This activity is seen on the left and on the right and goes from the posterior head region all the way through to the anterior head region. On some occasions, there is a somewhat triphasic morphology here demonstrated with the arrow, with an upgoing first phase, a downgoing second phase, and a finally upgoing third phase. In this EEG, however, there are some phase reversals, albeit without spike slow wave morphology to accompany them, and the dominant feature essentially is sinusoidal theta activity. There's some waxing and waning with periods of suppression between the theta activity, and as we go through the remainder of this segment, we can see largely sinusoidal theta of medium voltage predominating the picture. Here at the end is again a somewhat more triphasic morphology seen before a period of suppression. In summary, this EEG shows a typical pattern of severe diffuse encephalopathy. It is viewed as representing both subcortical and cortical dysfunction. This pattern is not etiology specific and can be due to a number of causes such as anoxia, hypoglycemia, and toxemia. Nonetheless, it helps the clinician differentiate epileptic causes of diminished levels of consciousness, metabolic causes, and even occasionally psychogenic unresponsiveness. This recording, showing a double banana montage, left over right, with parasagittal in the first 8 derivations and temporal in the last 8, shows a particular phenomenon. Here, outlined with the black arrow, is a sharp and then a slow wave morphology. There is a phase reversal, and it occupies a field that goes all the way from the frontal to the occipital derivation. This therefore exhibits epileptiform characteristics. There is some volume conduction of the slow wave all the way through to the posterior temporal region. Also, we notice that there's some 12 to 14 hertz sinusoidal alpha-beta frequency seen over both frontal regions. This probably represents sleep spindle activity, and therefore this ictal discharge is occurring during stage 2 sleep in this case. Further on in this 10-second segment, we can see that there is polymorphic 4 Hz theta and 3 Hz delta activity, in effect theta delta activity, representing focal slowing in the same region that there is this epileptiform discharge. We notice the absence of muscle artifact as this patient remains in sleep and has not been aroused by noxious stimulation. Moving on to the next 10-second segment, we can see that the focal slowing continues in a waxing and waning pattern over the right frontal region, as does some sleep activity in the form of spindles. Now, however, we see the appearance of blunted waves more frequently in the same region that the epileptiform discharge was seen previously. And in the first 5 seconds, 5 such potentials have appeared of varying morphology, but essentially all on the theme of field with sharp or blunted slow wave characteristics. This epileptiform discharge, as we go along, continues as the patient is aroused, as witnessed by this muscle artifact, and keeping our eyes on the right frontal region, we can see the repetitive nature of this discharge about 1 every second or so throughout this 10-second segment. It continues on in the subsequent 10-second segment, but as we get towards the end and the patient is no longer stimulated, we will see this right frontal discharge abate. On this page, again, you can see the clear epileptiform morphology is sharp and slow wave. Here, the sharp component is upgoing, as it is, in fact, in the next derivation, suggesting that this is an end-of-chain phenomenon in which there is no phase reversal to help with the determination that this is epileptic in nature. This upgoing component here indicates that at FP2, the discharge is surface negative, the negativity appearing in the first electrode of this electrode pair. We will now go towards the end of this segment, and we can see here in the last 10-second segment that the sharp slow waves are appearing now only every 2 to 3 seconds. This phenomenon in which arousal brings out epileptiform activity is called SIRPIDS, S-I-R-P-I-D-S. SIRPIDS is an acronym for stimulus-induced, rhythmic, periodic, or ictal discharges. This is a recently described periodic discharge which does evolve or change with the state of the patient, in other words, sleep versus arousal. It is not clear what is the optimal management for SIRPIDs and whether they represent more an interictal versus an ictal phenomenon when we think about management approaches.